Let's go ahead and get started with our new unit. Our new unit, as you might be aware, is exponential and logarithmic functions, and these are topics that may have been addressed, at least the exponential side, in Algebra 1. However, the logarithmic piece is the new piece that's added in to Algebra 2. But no worry, even if you didn't see it, we'll go through all of the topics as necessary. But prior to doing that, we are starting by thinking about ways we can combine functions of different varieties in different ways. At this point in the year, we've seen several different functions, some linear functions, absolute value, quadratic, polynomial, rational, and two different types of radical functions, the square root and the cube root. Much like with numbers, we can combine these functions in several different ways. We can add them together, we can subtract, we can multiply and divide all these different types of functions. And we'll even introduce one new type of operation in this unit, or at least at the first part of this unit. The sum function is defined as adding those two functions together, and it has a very specific notation. Much like f of x, for that function all alone, f is its name. The name of the sum function is f plus g. So if I wanted to find what f plus g of x is, I can evaluate each individual function at x and add them together. Same for the difference, noting that the order does matter in this case. Um, the product function is called f times g of x, and it's defined as the product of the two functions evaluated at that value, um, as well as the quotient function. F over g of x is equal to f of x divided by g of x, so long as that x value that I substitute in does not allow a denominator of 0. So let's look at what an example of this might look like. Suppose I have some function f of x is equal to x plus 1 and a second function g of x is equal to the square root of x plus 3. I want to find each of the following. The first thing I want to find is the sum function. It's defined as adding those two individual functions together, which means that the sum function is just x plus 1 plus the square root of x plus 3. There's no trick here, that it's very straightforward. If I wanted to evaluate that sum at the value of 6, I could do that in one of two ways. I could either use the first approach of taking that sum function we defined here and substituting 6 into it and going through the process to find that when I evaluate and simplify, it gives me 10. Or I could take advantage of the definition of what the sum function is and say, well, find f of 6, find g of 6, add them together, and that'll give me f plus g of 6. Which is exactly what's done in the second approach. And as you might note, those two values are the same. Uh-oh, Notability froze. It's been happening a lot lately. I don't know why. I don't know what to do about that. So proceeding forward, uh, a second example might be, given that f of x is equal to x squared minus 4 and g of x is equal to x plus 2, find each of the following. Again, this is very straightforward. You just define f plus g of x by taking each function and adding it together. Going through that process, I'll find that f plus g is equal to x squared plus x minus 2 by combining like terms. F minus g of x is evaluated in the same way, found in the same way, that it's f of x minus g of x, paying attention to that order, and paying attention to as well that I'm taking the entire function f of x and subtracting the entire function g of x, meaning that that negative here does get distributed to both terms in the second term, or in the second function. So when I distribute that negative, I end up with x squared minus x minus 6 when I go through the process of combining like terms. F times g of x is f of x times g of x. I can multiply each of the individual f of x and g of x functions, FOIL it out, and what I end up with is a cubic function, x cubed plus 2x squared minus 4x minus 8. These are fairly straightforward operations. It's not intended to trick you. And f of x divided by g of x is equal to x squared minus 4 divided by x plus 2, which you can factor the numerator and divide any common factors. That won't always be the case, but if you can, it will be expected that you do that. Um, and you have to keep that restriction that the denominator cannot be a value that would make it 0. So you add in that restriction so that it's not allowed. It's an excluded value of that expression. That's all I want in this first video. Actually, no, let's proceed forward. Um, Adding, subtracting, multiplying, and dividing is fairly straightforward with different types of functions because you're just combining them in ways that you've studied before. But in the real world, one additional operation that enters the picture is called function composition, in which I do some stuff with one function, and whatever that output of that first function is used as the input for the next function. That's exactly what composition of functions is. And it has a very weird notation, but that's just what's consistent and what's used. People tend to say fog x, but that's not appropriate. That's not correct. It's f of g of x, f of g of x. And saying it that way tells you exactly how to evaluate f of g of x. I take g of x and I stick it inside of f of x. That output of g is what the input of f is. That if I want to think of this visually, there's a diagram that I start with this x value and I substitute it into the inside function. G and f are just arbitrary names, by the way. I substitute it into the inside function and get some value out from that. And that value that I get from evaluating the first function, the innermost function at x, is then used to enter into the f, the outermost function, and the output is f of g of x. That x goes into g, and then g of x goes into f. So what might this look like as an example? Given that f of x is equal to 2x minus 5 and g of x is equal to x squared minus 3x plus 8, f of g of 7 can be found by first thinking about this in terms of the definition of function composition, that this is f of g of 7. So if I want to find what f of g of 7 is, I first need to find what g of 7 is, and that's what this aside is over here. Well, g of 7 is, plug the 7 into this defined g of x here, and once I simplify, I end up with g of 7 being 36. Now that I know g of 7 is 36, that 36 is the input of f. That output of g, or the output of the innermost function, is the input of the outermost function. F of 36 I find by taking the 36 and substituting it into that expression, leaving me with 67. Function composition, the order also does matter. So g of f of 7 would look different, that this is defined as g of f of 7. So in order to evaluate further, I need to first figure out what f of 7 is. F of 7 is 2 times 7 minus 5, and simplifying that gives you 9. 9 then is my input for the outermost function. So g of 9 would be 9 squared minus 3 times 9 plus 8, just because that's the function g here. It's that function. And when I simplify that, I get that it's equal to 62. Note that those are not the same value. This should be convincing evidence that, at least in this broad general case, that order does matter of composition. Which function you evaluate first does matter, and it always should be that of function, the second function that you're evaluating at that x value of 7 first, or that x value first. Uh-oh, Notability froze again. What's going on, Notability? This app is just glitchy. I gotta find another way to do this. That being said, that's one particular case in which I can get an x value of a specific number. What if I want a general expression Well, I can use that same idea that f of g of x I can write an expression for by taking g of x and substituting it into the expression for f of x. That anywhere in f where I would see an x, I replace it with g of x. And once I replace that with g of x, I can substitute g of x's expression into the equation and simplify from there. Once I simplify, I have my expression for f of g of x. The same goes for g of f of x, that I can find g of f of x by taking f of x and substituting it in anywhere where an x would be in the equation g of x. And from there, substituting f of x into the expression in this step, and then simplifying as much as possible to get g of f of x. There's not much more that can be said about composition. We can talk about the domain, but that gets really dicey. So I'm going to lateral past that domain question for now. I do, though, think it's good for us to assess whether or not we understand what function composition means. And so I think it's good to see a table like this. We don't often see tables in math as much as we should, but this is a perfect time for us to see how to use tables to evaluate function operations and do some composition stuff. So for instance, if I wanted to find f of 2, the way I would read this table is first go to the row that represents the function that I'm looking for. I'm looking at f of x right now, and I'm evaluating at an x value of -2. So f of -2 is where those two, the row and the column, intersect. F of -2 is -1. That's how that should be read. So in this case as well, g of 1, I go to the g row and to the 1x value column, that g of 1 is -2. I can combine these operations to produce some expressions like I did earlier, some operations on functions. H of 0 plus 2 times f of 1, that should be h of 0 is 2, there it is, plus 2 times f of 1, and f of 1 is here, meaning that when I simplify, it's 2 minus 6, or -4. F times g of 3 would be defined as f of 3 times g of 3, meaning that I need to find f of 3 and multiply it by g of 3. Well, f of 3 is -2, g of 3 is 2, -2 times 2 is -4, and that's exactly what's shown there. And it's the same idea that we're implementing every time, that I identify any of the pieces that I need from the table and use that to evaluate the function and simplify. I do want to step into, I'm going to skip the number 5 and number 6 just because they're fairly straightforward, and go immediately to number 7 here, f of g of -2. By the definition of function composition, I first should find g of -2, and whatever that output is, use that as the input for f. So g of -2, that would be 0. G of -2 is equal to 0, so that's my input for the f function. So I'm finding now f of 0, that's equal to 3, and that's what I should get as my value for f of g of -2. The same thing for g of h of -1. First find h of -1, whatever the output for that is, it's the input for g. The average rate of change in this, I'll want to remind you that it's f of b minus f of a all over b minus a for some given function on that interval. And then the second question is, for what x value do I get when I add these two functions? I get the value of 4. Well, f and g is what I'm looking at. And I can almost, with a table, just go through and add these piecewise or component-wise. Is 2 plus -1 equal to 4? No. So it's not the x value of 3. These don't add to 4. 0 and negative 3 don't add to 4. 3 and 1 do add to 4, so 0 is one of those values. Negative 3 and negative 2 do not add to 4. 3 and 1 do add to 4, so 2 is also a value where f plus g would equal 4. And these also don't work. So what is my solution set? For what values of x does f plus g of x equal 4? 0 and 2. I'm going to skip this next example. It's going to be in the notes, but I'm going to skip it because I want to jump into the last piece of taking a given composite function and breaking it into two pieces. What are the original functions that were used to compose it? I like to address this question just because there are many ways in which this problem can be worked, that there's not always one set answer because it depends on how you define your functions. What your general process should be is if I'm given a function and I want to find an f and a g such that that function that I'm given is equal to f of g of x, then what I need to find is an inside function that will be g of x and an outside function that will be f of x. That the outside function is whatever I would take and plug g of x into, I should get f of g of x. In just looking at this, it's easy to start with the inside function. For me, I instinctually would say that g of x could be x plus 4 because that's inside a square root. If that's how I define my inside function, then my outside function should be whatever I would need to plug this into to get the square root of x plus 4. So my outside function should be the square root of x. I want to note that that's not the only option to give you the correct answer, but that's one of the options. And that's the same idea for this second piece. First, start by defining your inside function. Not defining, I guess, but identifying what the inside function is, and then letting that determine your outside function. Here, to me, instinctually, it makes sense to say that the inside function would be 2x minus 3. What do I plug that into to get the outside, or this overall function? I would plug it into x to the 5th. And it's the same idea going forward. That's all we'll go over operations of functions. If you have additional questions, feel free to walk through the notes or send me an email. This is a very straightforward part of the unit. We'll jump into some more rigorous stuff as we proceed forward.